yeah, so just to recap, so we have these two notions of regularity, alpha, beta. We try to solve the resolvent equation. In the alpha variable, we lose 3/4, we gain 1 back, so that's okay, map back to alpha. But we cannot make up for this loss in the beta regularity. So the regularity with respect to n, so the decay of the kernels. And so the question is, if we can somehow trade in regularity in this sense against regularity in this sense. We only lose 3/4 here, we gain 1 here, so we have this to spare actually. We have something to spare and we would like to trade it to gain something in the n variable. And of course, in general, you cannot do that. But if we go to Fourier modes, then it is quite easy to see how we can do that, because it suffices to truncate to the large Fourier mode. So let's define this operator. The truncation pi to the large Fourier modes of phi evaluated in k is just taking the kth. So the Fourier mode evaluated in k is just the usual kth Fourier mode multiplied with this indicator function, which sets it to 0 if the k is not big enough. So we need 1 plus k squared to be bigger than 1 plus n to the 6th. And then we can see the following. So now we want to use this regularity which we have to trade in against the regularity in n here. So, and this, in the end, it will come out that we can exactly trade in these operators. So that's the result of the computation, and the computation is just 2 steps, so let's do it. So just multiplying, writing out what this is, we see that here we get 1 plus n to the 3, so this thing here squared. Here we get up to some 2 pi factors, 1 plus k squared. So we have minus 1/4 here, so this becomes minus 1/2 when we look at the square. And then we have the indicator function coming from here, which I just write at the summation index. So we have to sum only over k's for which this is satisfied. And if this is satisfied and we have a negative power here, then we can bound this term by the right-hand side to the minus 1/2. So we can bound this term by 1 plus n to the minus 3, which cancels directly with this term, the 1 plus n to the 3. So these two terms are gone and we remain with this part here. And now, we can instead sum over all k, get rid of this indicator function here, and in that way we get the L2 norm of phi squared. So through this operator here, we are able to trade in, and now, I mean, in principle, you can trade a certain amount of regularity in this sense against a certain amount of regularity in this sense. And here I already tuned the indices so that it fits exactly with our problem, because we have this to spare and we want to trade it against this. And you see that this is really a subcriticality argument. So when we want to do critical equations, we have to do something else, because this, so in the end, there will be, when we talk about fractional burgers, there will be some theta. And right now we're looking at theta equals to 1. And the critical one would be 3/4. And this 3/4 corresponds exactly to this 1/4 here. Right now we still have 1/4 left. So if we go from 3 to 3/4, we don't have anything left anymore. And once we don't have anything left anymore, we cannot use this argument to gain something. Right, so this works as long as theta is bigger than 3/4, because then we have a little bit left here. Okay, it's not so clear what happens if I change the theta, what happens at that point, but somehow we will see it more carefully, but this will happen exactly, that if you change the theta, you will have somehow the difference of theta to 3/4 left here, essentially. And then you can still trade it in by such an argument, but once the two are equal, this doesn't work anymore. But while it is subcritical, it doesn't really matter. It wasn't important that it was 1/4 here. If it would be minus 0.001, it would, I mean, then you would just have to choose a bigger cutoff here. It wouldn't really change anything about the story. Well, right. If we don't cut off exactly in 1 plus n to the 6, but we put an m here, then we could bound this thing here by m to the minus 1/2. We would get an additional m to the minus 1/2 here. And so we would pick up this factor m to the minus 1/2. And we will need this on the next slide to get a contraction in this, in the equation we will look at on the next slide. Right, so let's now return to the resolvent equation. This was the equation we wanted to solve. So this operator, lambda minus L, acting on phi is equal to psi. And now we change that equation. The first change we make is we get rid of the G and we put the projection of G on the large frequencies. Our hope is, and this will turn out to be true in the end, that the singularity which we see in this G plus operator, so the point that we cannot spit out a function, but we only get a distribution, is coming from large frequencies. So if we somehow manage to get rid of the singularity of this operator, maybe this could already remove all of the singularity of G. So maybe only this part carries all of the singularity of G already. And then it turns out that once we replace the G by that, we can actually remove the lambda here. So it is a bit conceptually easier. The following considerations will become easier if we have lambda equal to 0 here. This is, yeah, I can quickly explain why we want, why it makes things a bit easier. So if we go back to this finite dimensional example, so we solved this equation, this resolvent equation for positive lambda, and then we saw that L of u is equal to lambda u minus f. So you see this lambda u on the right-hand side. It would be much nicer if this term would be 0, right? Then you would just get f. And now after we replace the G, we can do this. So at least get rid of this lambda. So it's just for aesthetics. You could also put a lambda, but since we don't need it, let's not put it. Here I just recall what this operator is. So G upper is taking G and then projecting after that only on the large frequencies. And so then the sort of resolvent equation we get now, or Poisson equation actually, because lambda is now 0, would be this one, minus L0 minus G upper, acting on phi is equal to psi. And again, we can rewrite this. Phi is equal to minus L0 to the minus 1, acting on G upper of phi, plus, and now this operator inverse acting on psi. And let's give this thing a new name. Let's call this phi sharp. And so what we want to find is a phi which solves this fixed point equation, where we have this operator here applied to phi plus a phi sharp. And now, yeah, the proposition is we can really solve this equation. For which phi sharp, we take phi sharp in h1/2 beta. Beta can be anything now. Depending on which beta we choose, the phi that we construct, the solution will also have this regularity beta. So if we choose 3 here, then we have regularity 3 here. Ultimately, we will need to take beta equal to 6. But the point is that now the beta is not important anymore because we just get out exactly as much as we put in, and this thing here is basically the right-hand side of our equation. So this thing we choose. So this we can choose with good regularity. However, in the upper variable, we only use 1/2. So for suitable m, this says, so the m is, just to recall, this number which appears here in the cutoff. We can find a unique solution to this equation in this space. And we write this map. So this, we parameterize the solutions by phi sharp, and we write this as k of phi sharp. And then k is a linear bounded operator from h1/2 beta to h1/2 beta. And actually, I mean, the proof, this is the proof, so it's really easy. We have to look at this operator here. And the first thing we note is that we have this pi upper in there, and we have this minus L0 to the minus 1/4 left. And in all of the considerations we do now, I treat 1 minus L0 in the same way as minus L0. Of course, this thing is a bit more, especially when you take inverses, is a bit more dangerous because somehow, so you cannot always invert this operator. This is like inverting the Laplacian in each chaos. And when can you invert the Laplacian? Well, exactly if there's no zero Fourier mode. And then you can invert it because we're on the torus, we have a spectral gap, so that's fine. And it turns out that we will not deal with any zero Fourier mode. So everything here is without zero Fourier mode. So that's why I treat this operator in the same way as 1 minus this operator, as 1 minus L0 to the minus 1. And so we have this 1/4 which we will not need. So we trade it together with this thing to gain some small factor in m. We saw that we gained something in m. We saw m to the minus 1/2 on the previous slide, but there were squares everywhere. So since now there's no more square, it becomes minus 1/4. And then we still have 3/4 left because we only used a quarter here. And we used it to trade regularity in beta. So we went from beta here to beta minus 3/2 here. And this stays the same. So this is this estimate for that guy that we saw on the previous slide. And now we use our estimate for G that we have. So this thing, now we don't use the estimate for G yet. Now we just use that this thing gains a 3/4 derivative in the alpha variable. And so we can bound this by G of phi and then here minus 3/4. Just because of this minus 3/4, they go here. And now we use our estimates for G. And since 1/2 is between 1/4 and 1/2, this is an admissible parameter. So we get that, and we saw that the G is losing exactly 3/4 regularity in this variable and 3/2 regularity in this variable. So we can bound it exactly by 1/2 beta. And this is the thing we want to have. And we have this small factor to play with. So if you choose m large enough, depending on the beta somehow, I mean, this implicit constant here will depend on the beta, but not too badly. But in any case, if the m is large enough, then we get a contraction and then we have a unit fixed point for this equation. So yeah, we can now solve this modified resolvent equation. So we wanted to solve the resolvent equation to construct a domain for the generator. Now we solve the different equation. Let's see if this helps us with constructing the domain. So first of all, we call now a phi in this space h1/2 beta controlled if it is in the image of this k operator where we apply the k2 elements in h1 beta, and actually beta should be 6, I think, but okay, we will specify the beta soon. So k again was k of phi sharp was a unique solution to this equation. Why do I put the 1 here? In principle, we have a solution for every phi sharp in h1/2. So I could put 1/2 here, but if we don't have 1 here, then in the next step, we will not be able to get the generator to map phi to L2. So if phi is controlled, then L of phi is, by definition, L is L0 plus G, so we plug in the definition. And now we use this identity here, and we use it only in this term. So if we apply L0 here, then this together just becomes a minus. So we see minus G upper, this is here. And then we have plus L0 of phi sharp, this is here. And then the G of phi is just coming from above. And now this is the key point. No? So now this thing and this thing has some cancellations, and it just becomes G lower, which by definition is this term, which is the projection of G of phi onto the small frequencies. And here we have L0 of phi sharp, and that's why I wanted to have 1 degree of regularity here, which tells us that we can apply L0 once to this phi sharp. Yeah, so this thing is okay. So this is, if beta is positive, this is in L2. We have a random variable here. So that part would map to our, would already be good for defining a domain. This thing we have to understand. So the question is this now better, or did we do all this analysis and now this here still spits out a distribution? But of course the point is that this is better because the singularity is now removed and this is now a much more regular version of G. Maybe I close the window for a minute because of the church bells. So now, yeah, we have to check that this here is in L2 if this beta here is big enough. That's what we want to check now. Well, for this we need a lemma. So before we had a lemma that said in pi upper, where we projected on large frequencies, we could trade regularity in L0 against regularity in N. Now we do the opposite story. I mean, it's completely symmetric, basically, telling that if you have this pi lower, you can trade regularity in N against regularity in L0. And this is good news, because here beta can be anything. So just by choosing this guy of very high regularity in beta, we can guarantee that this guy has very high regularity in beta. And if we can trade this regularity in beta against regularity in L0, we can hope that this thing maps to, because here we have this projection on the small frequencies, that this thing maps to L2. And the proof is basically the same. So pi lower, you can also write in terms of the operator as the indicator function that 1 minus L0 is less than 1 plus n to the 6. And by the way, this way of seeing it, of really writing it in terms of the operator and cleaning up the analysis, is actually from the paper by Massimiliano with Mattia Tura. In our paper, some things are quite messy because we really do a lot of computations, and we don't really write it in this way. I'm not sure, we get a bit more information than you get out of this story. I'm not sure if you need this more of information. I had the impression that yes, at the time of writing the paper, but now I'm not so sure anymore. And anyway, in any case, for this talk, it's much better to present this cleaned up, nice way of doing things. So just see it in terms of the operator. Well, if we have this, the m you can now basically ignore. The m was before for getting a small factor. Now we just want to show that something is finite. We don't care if there's a large factor depending on m. So it will just be some constant. So this you can ignore. And then this here means that we can get 1 degree of regularity. Yeah, so we have this estimate. So if delta is positive, then the H alpha beta norm is bounded by the H alpha minus delta norm plus 6 delta here. So we can use 6 degrees of regularity in beta, this thing here, to trade against delta degrees of regularity in this variable, just by this relation here. And as a corollary of that, we get the following estimate for the G lower, which is the concatenation of this thing with G. The H0 norm of beta minus 6 is bounded by the H1 half norm of phi of beta. And how does this work? Well, we first use this estimate here to get rid of this term, and then we gain 1/4 regularity in the upper variable. We have to pay 6 times this in the lower variable. So 6 times 1/4 is 3/2. So we lose 3/2 here. And now we use the estimates for this guy here. So minus 1/4 is 1/2 minus 3/4. 1/2 was in the range of parameters that we can plug in. So we can estimate this by the H1 half beta norm. And so this is what I claimed. So to summarize, if phi is controlled with a beta which is bigger than 6, so this means phi sharp is in H1 beta and beta is bigger than 6, and phi is k of phi sharp, where k was this solution operator for the somehow modified resolvent equation, then this element is in H1 half beta, where this is still bigger than 6, and L of phi is L0 of phi sharp plus G lower of phi. And this thing here we already saw is in H0 of beta because we just lose one derivative in the upper variable by L0. And this thing here, by the computation we just did, is in H0 beta minus 6. And so since beta is bigger than 6, also this is positive. So the right-hand side is in L2. So we define the domain of the operator as the controlled elements with input in H1,6. So we take a phi sharp in H1,6, put it into this solution map K, and after that we get an element which is mapped to the domain by the generator. These functions are very, very complicated. No, they're not so simple functions on the space which we could try to plug into the operator would be like cylinder functions or something with a finite chaos expansion or so. And we saw that these sort of functions cannot be mapped to, cannot be in the domain. So if we plug those into the operator, then they're mapped to distributions. To find something which is mapped to a function, it has to have a very specific structure. It has to be very adapted to the operator. And in particular, it will always have an infinite chaos expansion. And yeah, so we can construct it only by solving an equation implicitly somehow. Okay, recap. Where did we arrive now? We constructed this operator through a chaos decomposition. And then we saw that if we take a nice phi, if we plug it into the operator, we get negative regularity. So in some sense, it's a distribution on an infinite dimensional space. Then we solved this sort of equation, which is a variant of the resolvent equation, where we replaced the operator G by this projection to the large Fourier modes, which allowed us to trade in the spare regularity in L0, which we had, against regularity in N. And in this way, we obtained a domain. So first of all, we solved this equation. And then we obtained a domain. Note that the solution to this equation only has regularity 1/2. So this means that L0 of this thing is not a function. L0 of this thing is a distribution, which then has cancellations with G of this thing, which also is a distribution. And so L0 of phi plus G of phi, this is a function. So really there are cancellations coming from both of these terms, which cancel the singular parts. Yeah, so L of this phi was given like this, L0 of phi sharp plus G lower. And in this way, we obtained a domain if the phi sharp is an H1, 6. Let's see, maybe I can continue a bit. So what do we want to do next? Now we have an operator. So far, we really, for our process, we didn't really get so far. No, we only constructed the operator now. Now we have to bridge somehow back to the real world, so to say. We have to associate this operator to a process. So we want to talk about the Martingale problem and whether solutions to the Martingale problem exist. Then, and this will be next lecture on Thursday, we will study uniqueness for the Martingale problem, and we want to understand the link with energy solutions. So maybe I can still go a bit further before we take the next break. So now I want to, for the rest of this lecture today, I will just...
Can I ask a question before?
Yes, yes.
So now you have defined this domain, but on that domain, the operator is probably not closed the way you wrote it, isn't it?
Yeah, because of this thing here is quite, I mean, okay, because you also have the 6. Yeah, probably not. No, probably not.
So do you have to worry about unique extensions, whatever, Markov uniqueness? I don't know.
No. We will get, no. So, I mean, I can define a Martingale problem for any operator. No, it doesn't have to be closed.
Okay.
And then we will study uniqueness by looking at the solution to the Kolmogorov equation. We will construct the solution to the Kolmogorov backward equation, and that then actually tells you that there exists a closed extension, which is a generator of a semigroup. And so in principle, this closed extension then is the full generator, but we don't need to describe the full generator. It suffices to describe it on a dense domain in order to make sense of the Martingale problem.
Okay.
And everything is so, yeah, this is more the discussion on Thursday, but so everything is, we make sure to keep everything concrete, to bring in as much abstract theory as we can, but always somehow keep the connection to concrete objects where these things somehow, yeah, where we don't need to apply some very abstract result to get uniqueness. Yeah, so I will tell you on Thursday. Giuseppe's question with his 3/4. So the argument is different. It's So we will not do this equation here. Instead, we do something else.
Oh, Nicolas, in some problems of particle systems, what people have done sometimes is that they play with the fact that you have G minus and G plus and they compose it somehow to get a little bit of the operator n.
Yeah. To gain, yeah. We will also do this. Yes. So this touches this aspect, which I mentioned at some point. So we have this estimate here. And here it is very important that we have beta minus 1, that we don't lose more than 1. And I think in this, so this is this graded sector condition, no?
Yeah.
And I think in this graded sector condition, they want to have a delta here, which is actually less than 1.
Yeah.
But for us, 1 is still okay, but it cannot be more than 1. So it's crucial to have a 1 there. And yeah, but then exactly with this G plus and G minus and this this is this Q symmetry, using this, we can gain 1 power in the n variable when we solve the Kolmogorov equation, which can make up for this loss. So it's quite subtle. And if really it would be bigger than 1, we would be lost. Which is surprising because in this construction of the generator, it doesn't play any role. We could have here beta minus 500 for all we care. So in what we did so far, it didn't play a role. But then when we want to study uniqueness, then yes.
Is there, sorry, can I just ask another question? Does this minus 1 loss in beta, does it correspond to the fact that the equation is quadratic, or?
Yeah, so if you have a non-quadratic equation, it would, I mean, I don't know how to answer this directly, but for a non-quadratic equation, let's say something quartic, then you would go up to 3 chaoses up. Mm-hmm. And you have to decay like n factorial. So pushing something 3 chaoses up is giving you already like a factor n to the 3/2 or so. And then, yeah, so you would probably risk losing a lot more in n. I'm not, you would have to do some concrete computations, but yeah.
But it's correct that this loss in beta is related to the homogeneity of the right-hand side of the nonlinearity.
Yeah, I mean, morally, yes. I cannot tell you, like, I didn't do a computation, but morally it should be related, yes.
Is related to, I'm not asking for a quantitative relation, I'm just, okay.
Yeah, so, and if you have some general nonlinearity, which is not a polynomial, then yeah, it's quite subtle to get anything.
Okay.
Okay, so we want to construct now a process which solves the Martingale problem for a generator. Okay, here just recall everything we had. So this is the definition of our space. This is the number operator. This is L0 operator. This K phi sharp solves this equation here. And if phi sharp is in H16, then L of phi is L0 of phi sharp plus G lower of phi. And this will be in L2. So actually, I mean, okay, here I'm a bit imprecise. Later I will be actually more precise than now. All of this is somehow on this Fox side. Of course, then after that, you can go back and associate random variables to it. But now here in this notation, I wasn't careful about that. I write things somehow identify the random variables with their image on the Fox space. So we say a process which has values in the space of distributions solves the Martingale problem for L if for all phi in the domain, we now have a domain, this thing here is a Martingale. And if you were very attentive and are not too tired at this late hour, and after listening to all these talks, you should protest now and say that this makes no sense. Because, I mean, yeah, these are functions that we constructed here, but they're L2 functions. So what we're trying to do here is we're trying to evaluate an L2 function in a point. And of course, we cannot really do this. So we have to, so this definition so far doesn't make any sense. This is why this is only 0.1. We have to add one more condition. Second condition is that the law of UT has to be absolutely continuous with respect to the white noise. And then if it is absolutely continuous, then this evaluation here makes sense, because this function is well defined up to mu null sets. But if we have this absolute continuity, then this thing doesn't see mu null sets. So in principle, this expression now would be well defined, but then you would still have to worry about this integral being well defined. And you would have to worry at a bunch of other places. So we want a bit more than that. And in fact, we ask that this sort of relation holds. So the L1 norm of phi of ut is bounded if t is between 0 and t by a t-dependent constant times the L2 norm of phi under the invariant measure. So this is the L2 norm of this random variable here. Yeah, the L1 norm of this random variable, and this is the L2 norm of phi with respect to mu. So this should be L2 of mu here. Which effectively, so once you have this relation, this tells you in particular that the law is absolutely continuous. So you can follow this relation because, well, you can just plug in an indicator function of a mu null set on the right-hand side, then this would be 0. And so the left-hand side would also be 0. And you would, you can also get from this, so we have the L1 norm here and the L2 norm here. So you can infer from this that the Radon-Nikodym derivative, because this thing here is just the integral of phi of u times d, this d law, d mu, and then d mu, right? So this Radon-Nikodym derivative has to be in L2 for this relation to hold. And so the L2 norm on the interval 0 to t has to be bounded by C capital T. And yeah, so under this assumption, we call this process incompressible, and then this integral here is well defined and everything here is well defined, and this condition now makes sense, and so this should become a Martingale. So the question is, do we have existence of solutions to the Martingale problem in this sense, and do we have uniqueness? Of course, Martingale problems only give you weak solutions, so it should be uniqueness in law, and of course also only after fixing the law of the initial condition, because here we didn't say anything about the initial condition. And we prove this by Galerkin approximation. So this is actually, I think I will mention it. So this was actually known before, essentially, at least this construction. So we use an approximation, and we use a very peculiar approximation, which is good for our purposes. So we take the equation we want to solve. We take already the full noise. We take the Laplacian here. The only difference is that we regularize the nonlinearity. So first, so what is this pi m here? Is the projection on the Fourier modes up to order k. So if we would sum over all k, then this here would be the inverse Fourier transform of the Fourier transform of u. So this would just be u. And so by truncating the sum here, well, we just project on the Fourier modes of order less than m. And then this thing here is a smooth function because it's a finite sum of smooth functions. So after we apply this projection, the square is well defined as the square of a smooth function. The derivative is well defined. And after that, the projection is again well defined. Why do we have to project again? Well, because multiplying two Fourier modes of order less than m together can, of course, give you a Fourier mode bigger than m. So that's why we project again after. Why is this convenient? Well, this equation has the same invariant measure. So this equation now, rigorously for the first time, is actually already invariant under the white noise. And how do we see that? This solution is a superposition of two processes, the sum of two independent processes, Vm and Zm. Vm is just the Galerkin approximation of our equation. So we project everything on the Fourier modes up to order m. So we project now also the noise, and we project also the initial condition here. And then since we have the projection out here, so everything on the right-hand side only has m Fourier modes. So we don't need the projection inside here anymore because at any fixed time. So this will already only have m Fourier modes. So this projection now comes for free. This is this part. But now we truncated the noise and we also truncated the initial condition to only m Fourier modes, and everything for the Fourier modes above m goes into this linear equation. Well, we also have the Laplacian here, and then 1 minus the projection. So only the large Fourier modes of the noise in here. And so this here, when we saw that the Fourier modes of this equation are all independent and the stationary measure are independent standard complex normals. So this is still true, except that now we only see these normals after m, so for k bigger than m. And here now you can do rigorously the formal analysis we did before to see that this also has an invariant measure, which are IID standard complex Gaussians for the Fourier modes. And this is up to order n because we have these projections outside here. And these two are independent because noises are independent. So the sum of the two will have now all Fourier modes less than m, bigger than m, and all independent. So that means we get that the law of the white noise is invariant for this equation now. And that's why this specific regularization is very convenient, because we can already work under this L2 of mu measure where we did all our analysis. Right, so the goal is to prove, I'm thinking where to take a break. Yeah, okay, let's go a bit further. So the goal is to prove tightness of this process. So to infer that there exist weak limits in some space, and to show that any limit solves the Martingale problem for our operator. Right, and then in this way we would have shown existence. So this is the classical program, how you would prove existence of solutions to a Martingale problem. The tightness is already done for this specific approximation in work by Max and Milton under the condition, and we will always impose this condition, that the density of the initial condition is absolutely, so the initial condition is absolutely continuous with respect to white noise, and the density is in L2. Actually, in this paper, the density is always 1, which is a fancy way of saying that they look at the stationary process, but if you look at the result in that paper, it immediately extends to this case. So the tightness is basically done. I will still explain how it works to you because it's a very nice argument, and which can be useful in other contexts. And then the second point is to show that any limit point solves the Martingale problem for L. This was not done in this work because this operator L didn't exist when this work was done. And the main ideas for that will be, first, it suffices to prove tightness of this infinite dimensional process. To prove that, it suffices if we show that tightness holds for infinitely many real valued processes. So we can test this process against phi, where phi is a smooth test function, prove tightness for this real valued process. And if we can do this for all test functions, then this sequence of processes with values in S prime of T, so in values of distributions, will be tight. And this is what's called Mitoma's criterion. And the second ingredient is the Ito trick, which allows us to remove the nonlinearity and to estimate this process as if it would be only an Ornstein-Uhlenbeck process. And estimating the Ornstein-Uhlenbeck process is easy, basically. And maybe this is a good point to take a break of 10 minutes, I think we have for the break. Or
10 minutes sounds good. So we say we do now until 35, and then you go to 5 past or 6 or something like that?
Yeah.
There's some questions from that Joseph.
I answered this question.
Oh yeah. Oh yeah, that was a much long time ago, right?
Yeah.
Okay, so bon appétit, bonne continuation.
Thanks. So yeah, we want to now show that the solution to this equation, which is well posed, is tight after being tested against the test function, and this will be done with this Ito trick. So I mean, this Mitoma criterion tells us we only have to look at the process tested against one test function. And then to prove tightness, we can apply the Kolmogorov continuity criterion, which gives us a control in some Hilda spaces, which are relatively compact. So the unit ball in the Hilda norm is compact in the space of continuous functions equipped with the uniform topology. So through that, we see that it suffices to prove such an estimate where P needs to be bigger than 2, right? Because this P and P half here is exactly what we see for the Brownian motion. And if you try to prove continuity of the Brownian motion by an LP estimate of this form, by applying Kolmogorov's continuity criterion, you need P bigger than 2. And this is the same here. So we need more than 2. 2 would not suffice. And for that purpose, we write this thing dynamically. So this is the integral over the drift. This is the martingale part coming from the space-time white noise, or derivative of the space-time white noise. And then this is the nonlinearity here. And for now, let's assume UM is stationary. At the end, I explain how to remove this assumption under the condition that the initial condition has an L2 density. So if this is stationary, then the pth moment is bounded by, of this thing, is bounded by t minus s to the p. Just pull the LP norm inside. And then use the stationarity, and then we get the LP norm of this random variable. This is a Gauss random variable, so its LP norm is its L2 norm raised to the p half power, raised to the pth power, times a p-dependent constant. So using the Gaussianity, we get a bound like this. So the L2 norm of this thing is, of course, by definition of the white noise, the L2 norm over the torus now of this kernel here. So the Laplacian of phi, second derivative of phi, and this is something which is finite. Here we have t minus s to the p, which is better than t minus s to the p half. P here can be anything, so this term is okay. Similarly, the martingale term, I mean, it's a Gaussian martingale, it's a space-time white noise. It doesn't depend on m, so of course it will be tight. And the estimate just, okay, I mean, you bound using Gaussianity or Berkeley-Davis-Gandhi inequality the pth moment by the second moment, and then the second moment you can compute. This is just t minus s to the, just t minus s, and then the quadratic variation. So this is a Brownian motion with quadratic variation given by the squared L2 norm of the derivative of phi, because the derivative of space-time white noise. And in this case, in this way, we get the t minus s to the p half, again, times a phi dependent constant, but we don't care. We just need to show that there exists some c phi here. So we don't care that it depends on phi. This term, however, I mean, for fixed m is easy to estimate. You can treat it in the same way as this term. You pull in the norm and then just estimate this using the white noise. But this will converge to the Burgers nonlinearity. And we saw that the Burgers nonlinearity is not in L2. It gives you something of negative regularity. So if we do this brutal estimate that we used for that term, we don't get anything here. So the question is how we can estimate that. And this is the story based on this Ito trick. So here we have to estimate an additive functional of the UM. And the additive functional is depending also on M, because we have these projections here. And so the question is how to estimate such an additive functional. And there are some tools from hydrodynamic limits which allow us to do this, and allow us to do this quite elegantly. And this is this Ito trick. And to explain this, let's first look at an SDE, just this equation. And actually, I don't know why I made it so complicated. So you should really think of sigma equal to the identity unit matrix, or think of just a one-dimensional thing. So then it would just be just one here. And we want to bound this expression. So an additive functional where we plug in now the solution to our SDE, rather than this complicated Markov process from infinite dimensions. And then we want to bound that. For now, we don't look at this at all. We just take some function g and apply Ito's formula to it. And then we see that g of xt minus g of x0 can be written as an integral Lg xs ds, where L is the generator, where this thing is the drift, and this thing here you should just think of as the Laplacian. And then you have a martingale term here, which you should see like that. And now, if, so far these problems had nothing to do with each other, and now the idea is to make these two terms the same. And we can do this if we can solve this equation. So if LG is equal to F, then we can bound this thing. This is then just LG here, so it's just coming down to bounding this term. We can bound it by g of xt minus g of xs, so now we go from s to t, which we can bound by the infinity norm of g. And then here we get this martingale, again from s to t, which we can then bound by t minus s to the p half if we take the pth. Okay, so there's a p missing here. And then there should also be a p here. P half. And then, well, whatever we have inside here, so this infinity norm of sigma and infinity norm of the derivative of g. All that is very simple, but now the point is that it gives you a deep result, and which is actually a bit surprising. So first of all, we now, in terms of time regularity, had something which was a drift, so which should be of order t minus s to the p. We treated it like being a martingale in some sense, so we get an estimate which is only of order p half. So somehow we see only that this would be 1/2 Felder continuous, so we gave up time regularity. On the other hand, we gained space regularity because solving this equation means somehow that we're inverting, because there's this Laplacian here. So just think of the Laplacian. Means we invert the Laplacian, so effectively we gain 2 degrees of regularity compared to f. So this thing, if f is in C alpha, the g will be in C alpha plus 2, and here we differentiate 1, so we're still in C alpha plus 1. So we gained 1 degree of regularity compared to f in space, but we gave up regularity in time. And this strategy we could also hope to implement for our process, right? There are 2 problems. The first one is that this equation actually, I mean, it becomes for our UM for which we want to prove tightness, for which we want to derive such estimates, it becomes this equation here, which with our tools now we can somehow solve, but it's quite difficult to analyze this equation actually, this LMG equals to F. I mean, even now when we looked into this resolvent equation, we didn't solve the full resolvent equation, but we solved this approximate resolvent equation. So to get a proxy for this sort of argument, we would have to go through the approximate resolvent equation and do some more analysis to then in the end get something which does the job. And there's another problem. I mean, we want to get some t minus s to the p half in the end, but actually this term here, which is coming from the boundary terms, has no time irregularity whatsoever. It gains even 2 space derivatives because g is in C alpha plus 2, but now we traded in all our time regularity against space regularity, and we have nothing in time left. And so this is a problem. So the way to go beyond that is the forward-backward decomposition. So the idea is to revert time once, and this will, in our case at least, get rid of both of these problems quite elegantly. So the point is that if you have a stationary Markov process with stationary measure nu, and this is now on an abstract Polish space, and you have the semigroup PT, which is defined as usually, then if you invert time, so you pick up some t bigger than 0, and then you let the process run backwards in time, then the time reverse process is again a Markov process, and the semigroup of this process is just the adjoint of the semigroup of the original process. And this is the adjoint in L2 of nu, where nu is our stationary measure. And so this is somehow a very basic, very general fact from Markov processes. But at least when I teach Markov processes, I don't tend to teach this. So maybe not everybody has seen that. So let's quickly give the proof, because the proof is actually very easy. So I give it here for 2 times. In principle, we would have to compute somehow expectations of such things for up to n times, where n is variable. But let's just compute it for 2 and then convince ourselves that after that we could iterate it to get more and more factors. So this expectation here, just plugging in the definition of x hat, is t minus t2, t minus t1. And now, actually, so before this was the smaller time, this was the bigger time. Now this becomes the smaller time because we subtract more from the final t, and this becomes the smaller time. This becomes the smaller time, this becomes the bigger time. And now by stationarity, we can shift everything by this t minus t2. So we get a 0 here, and T2, well, the difference of these two, which is T2 minus T1 here. Now we use the Markov property to write this thing. I mean, we condition on F0, and then we can pull in the semigroup here. So this becomes T2 minus T1 of F1. And this is F2 still here, and we have to integrate this using the stationarity also with respect to this measure nu. Now we pull this over. And that's the definition of the adjoint. We pull it over onto here, we get P star. And now we use, again, the stationarity and the Markov property to see that we have this relation here. So this is right. So yeah. Okay. So, okay. I don't. Maybe we ignore this instruction. See, how can we? So the only difference is that now I bracketed this thing and I hit it with this P star here. Well, this is the same as pulling the P star on the remaining factor here. The remaining factor is 1. And PT of 1 is, of course, because the Markov semigroup is conservative, PT of 1 is 1. So this P star I can always generate somehow out of thin air. And so in this way, we have proven this identity here, which is basically the Markov property of this time reverse process with these semigroups P star. So now you would have to do this for n times, and then you would see that you really have the Markov property with this P stars coming in. And so therefore, the X hat has the generator L star, because so L star is the adjoint of L now of the generator. So L is the generator of X and L star is the L2 new adjoint of that. Well, if you differentiate this adjoint semigroup, then you get the adjoint of the generator. And we define now the symmetric part of the generator as 1/2 L plus L star. And the antisymmetric part would be L minus LS, but we don't really need this. We will not see this. Okay, we define this. And then if we can solve now the equation that the symmetric part of the generator acts on F, acting on G is equal to F, then we can apply Ito's formula for the forward process, or the Martingale problem for the forward process. And we get this identity. So gxt minus gx0 is equal to this integral plus a martingale. And we can apply the Martingale problem for the backward process, which says that g of x hat t minus g of x hat 0 is equal to this integral here now with the adjoint operator plus a martingale in the filtration of this thing, which is a martingale in the backward filtration. And now we add these two terms. So this here is just xt. This here is x0. So when we add them, this cancels with this cancels with this. The boundary terms are gone. And here we have L plus L star, which is just twice the symmetric part. So this becomes twice LS, but LS of G is equal to F. So this just becomes twice FXS ds. And then this is this difference of these martingales, one going forward in time, one going backward in time. So now we were able to write such a quantity here as a sum of two martingales. The boundary terms are gone because they canceled from this addition. And we don't have to solve the equation LG equal to F, but it suffices to consider the equation where the symmetric part of the generator appears. And in our case, the symmetric part of the generator is the Ornstein-Uhlenbeck operator, is L0, because the G part I told you is skew symmetric. So this is going exactly into this LA here. And the L0, on the other hand, this I didn't tell you, but this is symmetric, well, because it's a Laplacian. Also, the Laplacian is self-adjoint. So that's why this one here is appearing in LS. And yeah, I told you the boundary terms disappear. So this solved, this story here with the forward-backward decomposition solved both the problems we had. So let's apply this for the Galerkin-Burgers equation. We need to bound this expression here, which is some Fm of um.
Nicolas, can I ask a question?
Yes.
So it looks a bit like all the specifics about the nonlinearity have now disappeared from your argument. So you only use that you have the right invariant measure.
Yes. So in this story, yes. So this story is very generic, yes.
So if you multiplied the nonlinearity with 1,000, it wouldn't change anything?
No. Because it would only change the anti-symmetric thing here. Would not change the estimate.
Okay.
No. And you could, I mean, on the level of the UMs, so you could think of not taking a quadratic nonlinearity, but taking something like in this Haber-Castell model where you take a generic function, basically. And if you do this in a way that is compatible with this Galerkin approximation, then this also works. This goes in the anti-symmetric part and then it's gone. In this story, I mean, then when you want to construct a generator, let's say in the limit, for example, you try to make sense of a general nonlinearity of your Berger's real equation, not truncated, of course, you have a problem. So there it's going to be important again that it's quadratic. But this story is generic, yes. And so this is, well, I guess one input in this Kipnis-Varadhan theme of proving, of studying fluctuations for additive functionals of generic Markov processes. So there's this thick book by Komorowski, Landim, and Oller, where these sort of considerations here are basically the starting point in chapter 1. And then they build somehow a whole theory from these sort of considerations, where for each process that you study, you still have to put in a bit more in order to control these kind of quantities and so, but in the end, everything is coming back to these sort of arguments. Of course, what is really specific here is that the symmetric part is so super nice, and really everything that we hate is sitting in the anti-symmetric part. This is quite peculiar. Yeah. Okay, so we need to bound this thing, which is some Fm of Um. So we need to solve L0 of Gm is equal to Fm. Fm is this thing. And this thing here is, I mean, this is how it showed up. So we applied Ito's formula to this equation where we tested this one against a phi. So this is Gm of W1 of phi. W1 of phi just means testing Um against phi. And therefore we automatically have estimates for this thing. So Gm is like G, only nicer, only truncated version of G. So every estimate that we have for G, we also have for Gm. And so uniformly in M. And so we have uniform estimates for this thing in some of our Sobolev spaces. Namely, that guy here is in H infinity, infinity, the intersection of all these guys. So this means this thing here, where we have the Gm plus and the Gm minus. The Gm minus will then also be in H infinity, infinity. But the Gm minus, the Gm plus can only output regularity at best -1/4 in the upper variable. So it is in H -1/4 infinity, this thing. But now when we solve this equation, we have to invert this operator, which gains 1 degree of regularity. So on the right-hand side, we have 1/4. On the left-hand side, we therefore get 3/4, and here again, infinity. So yeah, this thing actually is super regular. It's not quite so regular that we can really apply then in the end L0 to it and output a random variable. So the right-hand side is not in L2, but I mean, yeah. So everything somehow is nicely under control. We understand this well. And so therefore, now we can, and the point was that through this Ito trick, we gain regularity in space. And so now we only have 3/4, which, and here we have only -1/4. Now we gain 1 degree of regularity, but this is for the solution to this. Let me go back to the finite dimensional situation because it makes more sense there. So now we showed that the solution to this equation has a certain positive regularity, but now in the Martingale, we don't really see the solution to that equation. We see a derivative of that solution. So we still need some regularity of this one so that this thing here is still a nice function. And that's what we will now see for us, except that I will not really write down the Martingale. I will brush over this part. So using the Berkeley-Davis-Gandhi inequality, after we solve this equation, which we can solve, we get that this is bounded by some Martingale, depending on this function Gm here, the quadratic variation of that to the p half. And also there's a lot of things happening here. So this would actually be a page to work it out, but it's not really adding any new ideas. So the point is, first of all, that the quadratic variation, first of all, you can reduce this, you can write this quadratic variation as an integral. You can reduce to a fixed time by pulling the norm inside this integral, the expectation inside the integral. And then this becomes an expectation under the white noise measure of something to the p's power or so. And this thing of which you take the expectation under the white noise measure has a finite chaos decomposition, because this thing has a finite chaos decomposition, and inverting this operator, well, this operator is diagonal on the chaoses, so therefore this also lives only in the second chaos actually. This one goes up one chaos compared to W1, so it's in the second chaos, and then inverting this one still stays in the second chaos. And so therefore bounding the piece moment is the same as bounding the second moment. And the second moment of the quadratic variation you can compute nicely using this Dinkins formula. Okay, so you have a nice expression for the second moment of the quadratic variation, and exactly that. So you apply minus L0 to the 1/2 to this Gn. So this is like so L0 is like a Laplacian, so this is like a first order derivative. So this is similar to what we saw in this Ito finite dimensional example, also a first order derivative. And we saw we have 3/4. Now we have 1/2 that we lose, so we still have 1/4 left, so we're good. So this now has positive regularity, the right-hand side is finite, and here we have our t minus s to the p/2, and everything is uniform in M. So that's what I said, that we have this estimate uniformly in M, because this 1/2 is less than this 3/4 we actually have. Yeah, so here you can, the exponents don't become so clear, but you see that you don't really need so much. I mean, you could give up a little bit of regularity, and actually you can, with this argument, you can prove tightness, and this was also done in this paper by Max and Milton. You can prove tightness also in supercritical situations. So in situations where the theta, the fractional parameter, is bigger than 1/2. And so theta equal to 3/4 is the critical value. So even in supercritical situations, you get tightness by this argument. Let me see if it makes sense to, yeah. Okay, maybe it's good to stop here. I mean, it's late and I can do these last things on Thursday. So now the next point is we can extract limit points. This I can still tell you that we can see that the limit points are energy solutions, and next time then I will explain how we can see that they're also solving the Martingale problem. Here I define now what an energy solution is. So we showed that if the initial condition is a white noise, then we have this estimate up to a constant which depends on phi and p, but we don't care. We have p/2 here, t minus s to the p/2, and this is for any p. So in particular, we can choose p bigger than 2, and this allows us to get tightness. And then by this Mitoma criterion, we have tightness tested against any test function. This means we have tightness of the distribution valued process, so we can extract convergent, weakly convergent subsequences. And now let U be such a limit of one subsequence. And then in these works, they showed that this U is an energy solution. So it satisfies the following equation: U of phi minus U0 of phi minus the regular part of the drift minus the limit of these regularized Burger's nonlinearities, now evaluated in U, not in UM. I mean, this is really the limiting process, gives rise to a martingale, and the martingale has the right quadratic variation. So this martingale is corresponding to a derivative of a space-time white noise times square root 2. The point is that we define the nonlinearity through a limiting procedure. And so part of the definition is that this limit exists, and it also has to be of 0 quadratic variation, and then some other technical conditions. But this is somehow how the solution is defined. In particular, this object inside here is not defined in the limit. It is only defined as the limit over the time integration. And I mentioned this already maybe in the first lecture. This process here is not of finite variation in the limit. It's basically like a martingale. So it has, in terms of Hölder regularity, it has 3/4 Hölder regularity. So it's better than a martingale, but it's definitely not finite variation. So this is due to the fact that this test function, which we plugged into the Burgers generator here, is not in the domain. I mean, somehow it would be equivalent, being in the domain would be equivalent to this thing being of finite variation, because, or at least to this thing being differentiable. Because, I mean, the definition of the generator is that it's the derivative of the semigroup. So semigroup is built by taking expectations. So if you take an expectation of the difference of this, you get expectation of these guys and then expectation of the martingale, but the expectation of the martingale drops out. And then, I mean, this integral you can of course differentiate if it's differentiable. So in this way, you would see that then this test function is in the domain, but since we know that this simple test function is not in the domain, it cannot be true that this thing is of finite variation. And to get something where this term would be really differentiable and really a drift, we then have to use test functions which are in the domain, and maybe I explain this next time. And let me stop here.
Thank you very much. It's a lovely talk. Anybody has a question? No? If not,
I have a question.
yeah.
Yeah. So when you talk about test functions, here, what you mean? I want to take a test function, a nice test function. You don't mean to take a test function phi here to plug into the ut of phi, or you mean something more complicated?
Yeah. So this is bad notation. So I should maybe call this f. Is this, so this f here should be really just, and this we can see. So this is really just a usual test function, and then this here we can see as f of ut, right? Where f of u, and this should also, I should have called these f, because the phi's are the things on the Fock space, so it's a bit confusing. F of u is just u tested against phi. Does this answer the question?
Yeah. So, yeah. So this actually, that is not in the domain, no? So this is not something you can use as a test function.
Yeah. So the domain is more complicated, and everything in the domain has an infinite chaos decomposition.
Yeah.
Because the G plus, I mean, whatever you plug in, the G plus generates something one level higher, which is distributional. So you need something on this one level higher to kill this distributional component. So that means you can never stop. So you must have an infinite expansion.
Nicolas, for the uniqueness, do you need to determine the Martingale problem to make it well posed? Do you need to test for every function in the domain, or can you relax that?
So this, not for every function in the domain, but for this somehow subset of the domain. I mean, this specific domain that we identified, on which we have an operator which ultimately will be closable. For now, we don't know anything. We just define some operator. But so these are sufficient. We don't need anything non-concrete. Because this, yeah, maybe I should have stressed that this domain that we defined there is dense. And actually, it is not immediately obvious to see that this is dense. But how can we see this? So let me see where we had this. So we have to solve this equation, right? And now the question is whether solutions to such equations are dense in L2. We parameterize them by these guys. These guys just have to have regularity. So, so these guys are dense. That's no problem. So basically, if we can show that by solving this equation, we can find a solution to this equation somehow which is close to this phi sharp, then okay, it's a bit confusing how I'm saying it. So the idea is to choose this cutoff here. No. So we had this cutoff M. Where is it? where is this cutoff M here? So we go to larger, we truncate to larger and larger modes, and by choosing this larger and larger, we can basically make this guy converge to 0, and in this way we only recover this part here. And that's how we can show that the domain is dense, by solving a slightly different equation where we send this M to infinity, then plugging the solution to this modified equation into our original equation, and see that it is still in the domain, that it solves now our original equation with a phi sharp tilde, but the phi sharp tilde still has the necessary irregularity. Moreover, the solution to the modified equation converges back to the phi sharp, and in this way we get the density.
Thank you. Hendrik, can we give a round of applause? Are you unmuting everybody? Is
I have,
everybody
I think,
unmuted?
already done that, so I think we should do that, yeah.
Shall we do a
So I think everybody has the right to unmute at least now.
Oh, I see. Okay.
Sorry.
Excellent.
So no, I think I have allowed it now, perhaps. Ah, no, no.
Oh. Okay. Good. Thank you.
Perhaps I'm not sure. Yeah, no, I think